Hello everyone. In this video, I'm going to go over determinant. Part 1, we'll see cofactor expansion. So let's consider the linear system AX equals B. A is m by n matrix, and the x is unknown column vector, and then B is the given vector on the right hand side of the system. So then we're going to assume that the m is equal to n. So A gonna be a square matrix, and we assume that the square matrix has A has inverse matrix. It means that A is invertible. Then we're gonna do left multiplication of inverse matrix A in the linear system. Then we're gonna get in identity matrix I. Then the right hand side will get the A inverse times a matrix B. So, but identity matrix times any matrix, including a vector, column vector, return itself. So the x left hand side becomes just x bar. I mean the column vector x, and the right hand side is. So now then, just take a look at the example when m and n equals 2. Let's say the entry of A, matrix A, is A, B, C, and D. Then A inverse is going to be 1 over determinant A times that matrix. Quite rearrange the entry of A. I mean the interchange A and D, and then put negative sign on the other entries B and C. Here determinant A is the formula is the AD minus BC, and then this is denoted by this the long vertical bar, then A B C D, and then to close that long vertical bar. We haven't seen we saw this one in other lecture, but the goal in this lecture is to find determinant for larger matrices and to generalize the determinant for m by n matrices. So what if the size of matrix A is larger than greater than 2? Okay, so let's figure out how to find the determinant for such a matrices. So let A be the 3 by 3 matrices. Okay, and then we wanna the use the we wanna figure out the formula for determinant for matrix a 3 by 3 matrix A. To do that, we're gonna use the fact that the inverse matrix, the matrix A is invertible if and only if determinant of that matrix A is not equal to 0. So then to use that fact, we are gonna reduce the A to echelon form. Okay, so it means that we wanna the transform the rewrite matrix A to the upper triangular matrix. Okay, so then we are doing that. So it means that we're gonna use the three law operations. So to make the all the lower entry to 0. So then we're gonna doing that we're gonna get this one. So and then the here we assume that matrix A is invertible. It means that the pivot number of pivot must be equal to the number of columns. It means that when you just reduce matrix A to the echelon form, then all of the diagonal entry must be non-zero. Okay, so then by the way, if you don't know the what is the echelon form or reduced echelon form, then just search the echelon form or row echelon form, or just watch the other video in this YouTube channel. But simply saying that we're gonna use the first row to make to make the all the lower entry to zero. Okay, so in this case, the to make a zero in the second row first column, we just what the we just multiply by a minus a to 2 over a11 in each column of the first row and add that row into the second row to make this one zero. Okay, so that's one of the row operations. So doing that, we can similarly we can do that in that entries. Okay, and then yeah, similarly we can do the that entry too. So right here. Okay, so the thing is this. Um, Let me see. Yeah. So now see that that's the diagonal entry in the third row, third column. So if C equals 0, then the matrix A has only two pivot, which means that A one will not have the inverse matrix. Okay, but that's the contradiction because we assume that A is invertible, which means that A has inverse matrix. So now C, by the way, the C is actually this, and then the C is not equal to 0. From here, we can get a formula for the determinant of matrix A. So this one, the formula can be rewritten as like this one. So C is equal to A sub 1 1 and determinant of that one. This is that matrix is called the submatrix of matrix A obtained from A matrix A by deleting the first and row and first column. Okay, denoted by A sub 1 1. And this is the determinant of sum matrix A sub 1 2, which means that this is sum matrix of A obtained from A by deleting the first row and second column. So which means that in a subscript, the first number represent the number the row index uh, deleted, and then the second index represent the column index, which will be deleted from matrix A to obtain the sum matrix. The third one is same. So in general, the notation sub matrix A sub ij by deleting the ith row and then j's column. So if you are still confused what that means, sub matrix, just take a look at this. So the A sub 1 1 means that what? So matrix deleting first row and the first column, right? So we delete first row and first column. And then this is the entry left over. So that's the sub matrix A sub 1 1. Okay. So then determine A gonna be A11 times determinant of that sub matrix and then minus A sub 1 2 times determinant of, then in this case what's the sub matrix A1 1 2, that's the this one and this one, all the columns, the by deleting first row and the second column, then we get the sum matrix. Okay, so combining that one and this one, we get the sum matrix A1 2. So we just the term A can be expressed as the A starting from A sub 1 1 through the all the way to the end of the first row A sub n 1 n, and then we find the determine the sum matrix, and then we multiply by the corresponding the entry in the first row A11, A12, A13 through the A sub 1n, and then sign of the each term is alternatively plus changed to plus minus plus minus. So in general we can express the change of sign alternatively as like this: minus 1 to the 1 plus j. So here 1 is the index row of index, and j is the index of column. Okay, so but the cell determine A, now we kind of formalize the determinant of A is like this. Okay, and the what but we can just you can choose the instead of first row, or we can choose the second row, third row, any row or column you can choose. Okay, once you choose the, for example, we can choose the second row, and then you just find the sub matrix corresponding a sub 1 2 through the a sub 2n. Okay, and then apply that formulas. Okay, instead of the sub matrix and then the entries, change to the entry in the second row and then the corresponding sub matrices, then still you can get the same value for the determinant A. Okay, but anyway, so this is quite a long expressions, but now we see the sign with the determinant of the sub matrix A is called the IJ cofactor matrix A. Okay, so the C sub ij, that means the minus 1 to the I plus j times determinant of some matrix A sub ij. That's the I comma j cofactor of matrix A. So I is a row index, j is a column index. So for given square n by n square matrix A, determinant A can be expressed as like this. So this is a short expression of that expression of determinant A. Okay, so this formula is called the cofactor expansion across the first row of matrix A. I told you um, you can make you can make the formula of the inverse determinant A, applying the cofactor expansion across not just first row but any row or any column. Okay, cofactor expansion down the first column, yeah, it works. And then across the maybe third row of matrix, yeah, it works. Okay, so cofactor expansion of determinant is this. So you can say that here it means that what see this is ith row. I told you. Okay, not just first row, but any row it works, and then any column it works. So the term A you can find the term A applying the cofactor expansion down the jth column. Okay, so this is the example. So that's the, by the way, this is the key, the main, the formula in this video. Okay, so let's say A is 3 by 3 matrix is given in this example. So the what you're going to do, I want to find out the term A using the cofactor expansion. So now you see I'll use the third row. Why? I apply the cofactor expansion third row. Why? Because third row has this is the row has the most zeros entry, right? So this one has 2 0. I know this third column also has 2 0, but I choose the third row. Okay, so I choose A3 comma 1 and then C3 1. You don't have to find the cofactor corresponding to A3 1 because A3 1 0. You don't have to find out this. Okay, this one also A3 3 0, so we don't have to take care of that one. So I will just find out the cofactor of A3 2, which is C3 2. Okay, so now then the determinant of A32 is what A32 gonna be what? So we delete the third row and the second column. So we're gonna get the sum matrix by collecting leftover the entries 1 0 0 0. See, sorry, the 1 0 2 negative 1. Sorry. Okay. So now, oh yeah, sorry. Let's see. Yeah, so there was a typo, so it should be 102 negative 1, right? So deleting third row and the second column, we got the 102 negative 1 right here. So then negative 1 to the 3 plus 2, which is negative 1, and the 8 sub 32, 8 sub 32 is going to be negative 2, and the determinant of this one is going to be negative 1 times 0, which is negative 1, so we got the negative 2. Okay, so here's the theorem. Determinant of triangular matrices um, going to be the finding determinant of triangular matrix is easier than finding determinant of the just regular square matrix. Okay, why? Because if A is a triangular matrix, then determine A is the product of the entries on the main diagonal of A. Okay, so which means that you see that here, this is the upper triangular matrix. I mean, lower triangular matrix is upper triangular matrix. Both the hold that theorems. Okay, so if A is a upper triangular matrix, then determine A gonna be in this theorem says that determine A gonna be product of the diagonal entries. Okay, why? Let's see. Since the determinant A is the applying the cofactor expansion, uh, uh, applying the cofactor expansion of matrix A, then we gotta find out a determinant of the submatrices. So I choose the first column, okay, and then for each entry, I'm gonna find out corresponding the determinant of the submatrices, okay. So then the first one, we're going to do this. Negative 1 to the 1 plus 1 times A11 and determine the A11. But determine A11 going to be this one, right? Let's see, right here. And by the way, what about the other, determinant of some matrices of other the entries on that first column? We don't have to find out that. Why? Because all the entries are 0, right? Because this is a triangular matrix. So we don't have to find out the determinant of the submatrices in this term because these are 0. Okay, so we only what we need to do is to figure out this one. Okay, so now then what's the determinant of the sub matrix A sub 1 1? It's gonna be, by the way, this is a sub matrix A11, and that is gonna be to find the determinant A sub 1 1. We choose the first column in this sub matrix, and that's gonna be sub matrix of sub matrix. So let's say this A sub 1 1 and sub 1 1. Okay. So now then to find out determinant of A sub 1 1 and sub 1 1, we gonna choose the first column again. That's the the sub matrix of sub matrix, and then what we choose the we have to find the determinant of that sub matrix. So this is A sub 1 1 1 1 1 1. Okay, right? See. Now then, by the way, what about the back to the second stage? What about the sub matrix of the all other terms? 0, right? The same region as this. Okay, all the entries in this column is 0. All the entries in this column is 0. So all other terms going to be 0. Okay. Now then, we got this. What? Doing that last one, we're gonna get this sub matrix A N N, right? Okay. So determine sub matrix A N N is A N N, right? So now what are you gonna then we can this one is equal to by the way, negative 1 to the 1 plus 1 is just a negative 1 squared, which is 1. Okay, then you see A11 copy down, and this one is gonna be just a product of A22 times through the AN. So this one, the capital letter pi represent product. Okay, you know sigma represent the summation, but this is a product. Okay, so we multiply a sub I while I goes 1 through n. Okay, so now that's why the triangle matrix determinant of the triangle matrix is the product of the entry diagonal entry. Okay, so that's for today.